All right, today we're just going to have a review session for our midterm. So we're just going to go over basically a bunch of problems that are like representative of the difficulty and type of problems that you would see on the midterm. So the first thing I just want to go over is like some exam info so that everyone's on the same page and we have everything runs smoothly. So there is a practice exam on Canvas. The solutions will be on the exam info page. You'll also be able to find the formula sheet on the exam info page. So this formula sheet is what you'll have on the exam. If you want to print it out beforehand and take like a hard copy with you to the exam, that's totally fine. There'll also be an exam formula sheet within the exam. So, for example, when you go into the exam, like the first question will not be a real question. It will just be like a text box with the formula sheet in it. So even if you don't take a formula sheet with you, there will still be all the formula sheet there. So you don't have to worry about that. And then for the proctoring, we're going to be using Respondus, as I said, but we're going to be using the webcam also. So if you don't have a webcam or you have issues with that, just let me know, obviously, beforehand. So hopefully everyone's used Respondus and the webcam, so you guys all know how to use that. But what I'm going to do a little bit differently is also have Zoom available. So I'll have the settings set on Respondus so that you can access Zoom during the exam. But you have to be a little bit careful. So if there's some kind of issue on Canvas, like if you're having trouble, there's just bugs in Canvas. So if you have any kind of trouble with the exam, viewing a question, or something's just not behaving properly, or if you think there's a mistake on the exam, a typo or whatever, this way you can contact me and you don't have to like go through the whole exam with possibly either a mistake or something not working on your end. So there'll be a link for a Zoom meeting in the top of your the instructions for the exam. So if you want to join the Zoom meeting, I'll obviously be there the whole time of the exam. So you can just join the Zoom meeting, click on the link. It will open up a new tab of Zoom. So you will have like a prompt where it will say, do you want to open the Zoom app? So since you can't actually open the Zoom app in Respondus, you have to click no. So no, do not open the Zoom app. Then that like prompt will go away, but you'll still be on the Zoom page. And then there'll be an option to join from browser. So then you just click on join from browser. I have a picture of this on the exam info page where you could see the join from browser part. So then you click join from browser and then you will join the Zoom exam via your browser and not the Zoom app, which you probably use most of the time. And then, that way you'll be able to contact me if there's any issue with your exam. So you can also use a calculator, and the exam will be similar to the practice midterm, 4 or 5 multiple choice, and then 3 short answer with multiple parts. Obviously, for the multiple choice part, we're not going to consider any work. There's no partial credit on the multiple choice. It's just whatever you put in there as your answer, that's your answer. There will be partial credit on the short answer, though. So you're going to be, for the short answer, doing your work on, a blank piece of paper. And then the most important thing is when you're done with your work and you're going to submit your exam, make sure that you enter in your final answer on Canvas. So for the short answer, let's say you get like 76 meters per second as your final answer. Circle that on your paper and then also enter in 76 meters per second on your Canvas quiz. So make sure that your final answer matches up with the answer that you input on Canvas. So your final answer that's circled on the paper and the answer you put in Canvas have to match up, and you have to input that Canvas answer. If you don't input your answers, we have no way of checking that you are actually submitting the work that you did during the exam. So make sure that you do that. If you don't enter in your answer on Canvas, it's just going to be a 0. So make sure that you circle that answer clearly and enter it into Canvas. Let's say if you don't finish a question, you only got partially through it, just circle whatever your last step is, however far you got, just circle that last step and then enter that into Canvas as well. You can enter in formulas. So if you didn't get all the way and you just have like a formula left, you can just enter that formula in. That way at least the TAs can just check that your final answer on your paper and your answer on Canvas match up. And so again, that's very important. Like I said, you will get a 0 on your work if you do not enter your final answer into Canvas as well. So you absolutely have to remember to do that. For the exam, I'm giving everyone an hour and 30 minutes. So normally we have an hour and 20 for the class. So now we're going to have an hour, an extra 10 minutes, an hour and 30 minutes, so that way you can just go over your answers, input them into Canvas, and you still get the full hour and 20 minutes to take the exam. And also just be mindful that there is a timer on Canvas, so make sure you keep an eye on that so you don't run out of time too soon. And the other thing is obviously write neatly. So make sure that's like probably the number one thing. is write as neatly as you can. Put all of your work in very like linear steps that the TAs can easily see. It's much harder grading online than it is in person. So you have to kind of, if like the TAs want to help you and give you partial credit, but you have to also help them and make it easy for them to see what you're doing. So they can give you more partial credit if they can very easily see what you're doing. There's over 200 people in the class, so the easier you make it for them to grade your work, the more partial credit they can give you, if they can easily see either where you went wrong or what your thought process was. So it's really important to write really neatly. Don't do things in your head or just like do a bunch of calculations on your calculator where if you enter in even just a number wrong, they are not going to know what you did wrong, and you're just going to get no points for that, even if you were close. So make sure that you write all your work really neatly. And the other thing is that you have to actually show all your work. So if there's no work shown for a problem and there's just an answer, that's just going to get a 0. So you absolutely have to show all your work. And you have to show, all the steps so the TAs can follow what you did. Don't just write one equation and then somehow get to the answer. We need to see all your work and how you got there. So then when you're done, so you're done with your exam, you've entered your answers into Canvas, you've submitted your exam, then what you're going to do is immediately take either a picture or scan your work and then upload it to the assignment called midterm work. And try to do that obviously right away. The sooner you do it, the better. If there's any, unfortunately, if there's any like long lag time, we don't want to think that people are cheating, but if, you take an hour to submit your work, like that's not going to look good. So make sure you submit your work as fast as you can. Within 10 minutes is reasonable. So make sure that you submit it as fast as you can. All right, so that's it for the exam info. So now we can get to the review. So the first thing I want to review is the phase shift that a lot of people asked about. So phase shift. So a phase shift is basically it just moves your graph to the left or to the right. So a little trig review, we know that cosine theta looks like that and sine theta looks like that. Now if I wanted to make my cosine graph look like a sine graph, I could just subtract pi over 2. So I could just do cosine theta minus pi over 2, and then it would look like this. Similarly, if I wanted to make my sine graph look like a cosine graph, I could just add pi over 2 to the argument. Cosine plus, sine theta plus pi over 2 looks like a cosine graph. So sine and cosine are related by a phase shift of 90 degrees, by pi over 2. So this is just a trig identity that cosine of theta minus pi over 2 is equal to sine theta, and sine of theta plus pi over 2 is equal to cosine theta. So that's why in some books or some resources you might see, while we had our simple harmonic motion looked like this, right? Cosine omega t. Some places might have their simple harmonic motion as sine omega t, and that's just because sine and cosine kind of like are the same thing. They're just related by a phase shift. So I could have, if I had a phase shift here of minus pi over 2, I could just as easily write my formula for simple harmonic motion this way. So that's all a phase shift does. It just shifts to the left or right, and basically it can interchange in some cases. It can interchange between sine and cosine. And now one thing that I don't really like about your book, that I think it makes it a little bit more confusing, is it leaves out the phase shift in a lot of formulas where there is a phase shift, and that can be confusing. So in our simple harmonic motion, like I said, we had x of t is equal to a cosine omega t, and there's a phase shift there. And they did include the phase shift when they presented this formula. Then when we did our traveling waves, so when we did our transverse wave, we had y of xt, and then we had a cosine kx minus omega t. And now there really is still a phase shift in there. So technically, if I wanted to write the correct solution to my transverse wave, I would have to include a phase shift there as well. But your book doesn't include this, which I think makes it a little bit more confusing, because you'll see other books that write sine here, and then it's not clear why some books use cosine and some books use sine, and it's because there's really a phase shift in here, and you can just shift between cosine and sine depending on, if you add pi over 2 or subtract pi over 2. So there is really a phase shift in here in our transverse wave equation. And then the same thing when we did our standing waves. So when we had our standing waves, and we had something like this, we had 2a sine kx sine omega t. There really is still a phase shift in here too, again, even though your book didn't include it. So really, there's another phase shift in here, because if we had when we had our, standing wave, you could have something that looks like this. But there doesn't have to always be a node here, right? We saw some situations where you can have an antinode there. And then, like, this equation without a phase shift doesn't really work to describe something that looks maybe like this. Because this clearly is not sine if it's starting at 1, right? That looks like cosine. So there really is a phase shift in here as well. I don't think we're going to be seeing any problems that actually make use of these two phase shifts in here, but just so you know, they are there. And I think that's where some of the confusion might be coming from. So all your phase shift does is just shift your plot to the left or right. All right, now let's just do a problem on power. So we have a piano wire with mass of 2.9 grams and length of 76 centimeters is stretched with a tension of 33 newtons. A wave with frequency 115 hertz and amplitude of 1.7 millimeters travels along the wire. And the first thing we want to do is calculate the average power carried by the wave. So let's write down all of our things that we have. So we have the mass is 2.9 times 10 to the negative 3 kilograms. So I highly recommend when you're doing problems to just immediately write down everything that you're given and also immediately switch them into standard units so that you don't make any unit errors. Okay, and then the length we were given was 76 times 10 to the negative 2 meters. The tension was 33 newtons. The frequency was 115 hertz. And the amplitude was 1.7 millimeters. Okay, now I want to calculate the average power carried by the wave. So this is just like a plug and chug problem. We just look at the formula for average power, and that is given by this. So this F is, we could write tension, doesn't matter, it's write F or T, omega squared A squared. So all you have to do is just plug these numbers in. We have the tension, we have the amplitude, but we need to find mu and omega. So mu, remember, is just the mass per unit length, so it's m over L. So we're just going to do 2.9 times 10 to the negative 3 divided by 76 times 10 to the negative 2, and we get 0.003 kilograms per meter for mu. Then we need to just find omega. So the angular frequency is 2 pi times the frequency, and the frequency is 115 hertz, so that gives us 722.2 radians per second. So now we can just plug everything into this equation. So we get that the average power is 1/2 0.003 and then 33. And then omega is 72.2 squared, and then the amplitude is 1.7 times 10 to the negative 3 squared. And then you plug all those things into your calculator, and you get 0.24 watts. Okay, so that's for part A. So for the power with a transverse wave, this is really as complicated as I'm going to give you, where maybe you have to like solve for mu or you have to solve for omega or something like that. I'm not going to give you anything too crazy with this kind of stuff. It's kind of going to be very straightforward, plug it into the formula, and that's it. So now here for part B, what happens to the average power if the wave amplitude is halved? Well, if the wave amplitude is halved, So then we'll have P average is 1/2 mu F omega squared. And now it's A over 2 squared, right? Well, now we can see that we're going to have an extra factor of 1/4 in the bottom because we have a 1/2 squared, so that will give us 1/4. So we'll have 1/4 times the original power. So it will decrease by a factor of 4. All right, now let's go on to a slightly more challenging problem. So this deals with the nodes and antinodes. So here we have adjacent antinodes of a standing wave on a string are 15 centimeters apart. A particle at an antinode oscillates in simple harmonic motion with amplitude of 0.850 centimeters and a period of 0.075 seconds. The string lies along the x-axis and is fixed at x equals 0. So the first thing we want to know is how far apart are adjacent nodes. So let's first just draw what we have here. So we have a standing wave. So a standing wave will look like that, and then, it will also look like that later. And then also, I got a question about when will you know if it's a standing wave or a traveling wave, and it will always just tell you that's a standing wave, or it might be like obvious from the problem if you say, let's say you have a wave or a string fixed at both ends here. This has to be a standing wave if it's fixed at both ends like this because there's nowhere for it to go, right? If it's fixed at both ends like this, it's going to be a standing wave. Okay, so we have a standing wave, and adjacent antinodes are 15 centimeters apart. So that means this is an antinode, and then this is the adjacent antinode. These are 15 centimeters apart. So right away we can figure out the wavelength from this, right? Because we know that the wavelength is going to be from here to here. So we can see that that's going to be just double this distance, right? So right away I'm going to write down that the wavelength is 30 centimeters. So how far apart are the adjacent nodes? Well, the adjacent nodes are going to be just as far apart as the adjacent antinodes. So you can see your antinodes are separated by 15 centimeters, and your nodes are also going to be separated by 15 centimeters, by half a wavelength. So the nodes are going to be separated by 15 centimeters. And again, that's because our nodes and antinodes on a standing wave are every half wavelength. You have node, 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 and every half wavelength you have antinode, antinode, antinode. All right, now what are the wavelength, amplitude, and speed of the two traveling waves that form this pattern? So the wavelength is going to be the same because when we have two traveling waves that make up a standing wave, the wavelength of them is the same. So they're going to have the same wavelength as your standing wave. And we can see that the wavelength here we already said was 30 centimeters. So the wavelength is going to be 30 centimeters. Then the amplitude of each wave. So the amplitude, they told us that an antinode oscillates in simple harmonic motion with an amplitude of 0.85 centimeters. So that means this distance here is 0.85 centimeters, right? But remember our equation for a standing wave. So for a standing wave, we had this equation. And we can see that the amplitude for our standing wave is actually twice the amplitude for each individual wave, because in a standing wave, they interfere constructively at the antinodes, right? So their amplitude will actually be twice each individual amplitude. So this 2a here corresponds to the 0.85 centimeters here. So each individual wave will have an amplitude of half this. So the amplitude will be 0.85 divided by 2, which is 0.425 centimeters. And also the reason that I knew that corresponded to the amplitude here when they say a particle at an antinode oscillates in simple harmonic motion, Remember we said for a standing wave, each particle along the wave actually oscillates in simple harmonic motion. So every single particle here is going to be undergoing simple harmonic motion in one direction, just up and down, wherever it is on the wave. And at an antinode, we know it's reaching the maximum amplitude, right? So this is the maximum, at the antinode, this is the maximum amplitude. So that will be twice the amplitude for each individual wave. And then we also want the speed of the two traveling waves. So the speed, we can just use this formula, lambda times f. So we know that lambda, we already found, was 30. The frequency, we can find because it says that the period is 0.0750. And we know that the frequency and period are just inverses of each other. So we can just rewrite the frequency as 1 over the period. And again, for a standing wave, the period of each individual wave will be the same as the period for the entire wave. So we can just divide 0.3, because it was 30 centimeters, so that's 0.3 meters, by 0.075, and we get 4 meters per second. And then you could also, if you wanted to use this formula, you could also use that too, and that's fine. Okay, so these are our answers for part B. So we have the wavelength is 30 centimeters, the amplitude, and the wave speed of each. So now we want to know, find the maximum and minimum transverse speeds of a point at an antinode. So we want to know what's the maximum and minimum transverse speed that this particle right here obtains. So for part C, now you can do it two ways. You can derive the answer, or if you just remember the formula. So if you remember the formula for Vmax for simple harmonic motion, it's just omega times the amplitude. So we could just use that formula where we'll have, let's see, omega, they don't give us the frequency, so we'd have to do, we'd have to do 2 pi times the frequency times the amplitude. And that would be 2 pi times 1 over the period times the amplitude. And so that will give us 2 pi times 1 over 0.075. And then the amplitude is the full amplitude here, right? Because this particle is undergoing simple harmonic motion with that full 0.85 centimeters amplitude. So that will be 0.85 times 10 to the negative 2, and that will give us 0.712 meters per second. And the minimum speed, and be careful here, they're saying speed, not velocity, so the minimum speed will be 0, and that will happen at this point up here, right? Because when it gets to its maximum amplitude, it has to stop and turn around and come back. So that means it's going to be going 0 meters per second at that turning point. So Vmax is this, and that, remember, occurs right here in the midpoint. And then Vmin, so the minimum speed, will be 0. And now you could do this another way as well. If you wanted to, let's say you didn't remember this formula here. What you would have to do then is do the derivative with respect to time. So remember our y of x comma t for a standing wave, we said was 2 times the amplitude of each individual wave, sine kx, sine omega t. So you'd have to take the partial derivative of this with respect to time. So that will give you 2a, we'll have an omega come out, and we'll have sine kx cosine omega t, and the omega comes from the chain rule in here. So then you say, okay, well, we're at some point, some antinode point. So the point along the x-axis is determined here, right, where the sine k, we have sine kx. So at an antinode, this term here will be equal to 1 because sine is at its maximum, so that means we're at an antinode. And then this cosine omega t will be the simple harmonic motion in one direction. So this cosine omega t is the simple harmonic motion going up and down this way, and the sine kx tells you basically like where along this axis are you. So the cosine omega t is what governs the motion up and down in this direction, so in like the time direction, and then the sine kx is what tells you like where along this x-axis are you. So at an antinode, sine kx is going to be equal to 1. So that it's at its maximum amplitude here. And then we know, okay, so for Vmax, that means cosine is also going to be at its maximum value, which is 1. And so then you can see here that we have omega times the amplitude of our standing wave here, which is what we had right here. And then for Vmin, you say, okay, well, the minimum value of this is going to be where cosine is 0, and then you end up with 0 again. All right, and then for, let's see, find the maximum and minimum. Okay, we did that. For part D, what is the shortest distance along a string between a node and, it says antinode, but I cut that off by accident. Okay, so between a node and an antinode, so we can just look here. And between our node and an antinode, we can see that this is going to be a quarter wavelength, right? Because we know from a node to a node, it's half a wavelength. So from a node to an antinode, it's a quarter wavelength. So we're going to have the distance is going to be lambda over 4. And so that's going to be 7.5 centimeters for our 30 centimeter wavelength. All right, now let's do another example problem with standing waves. So we have standing waves on a wire are described by equation, that's just the equation for a standing wave, with the amplitude, so the standing wave amplitude is given by this. We have omega, we have k. The left end of the wire is at x equals 0, so that means our wave, is down here and is going like that. All right, and we want to know what distances from the left end, so from this x equals 0 end, are the nodes of the standing wave and the antinodes of the standing wave. So let's write down, we have our y of xt is this amplitude, so it's 2 point, I'll just write it as the amplitude of our standing wave. So that's twice the amplitude of each individual wave that makes up the standing wave. Then we have sine kx sine omega t, and we're given omega. Okay, so we're given everything for this wave. So let's do the nodes first. The nodes are, we know one node is at x equals 0. Then we have another node here and here. And then, it goes on down the wave. It could go off to infinity. So a node is going to be a place that never moves from 0, right? The location of this along our axis here is always 0, right? It never goes up or down. It's always right here. So that's going to be governed by, like I said in the previous problem, this term here, right? The position is always going to be 0 on the y-axis here. So the nodes are going to be somewhere where sine kx is always 0. And now where is sine always 0? Well, we draw a sine plot. We have it at 0. It's 0 again at pi. It's 0 at 2 pi. It's 0 at 3 pi, and all the way down. So sine is 0 when we have an integer number of pi's. So when you're doing sine of n pi, where n is some integer, sine will always be 0 there. So sine of n pi is always 0. So that means that kx has to be equal to an integer number or an integer multiple of pi. So kx has to be equal to n pi, and then we'll just solve for x. We get x is equal to n pi over k. And then we just plug in pi and k. So we were told that, let's see, n is just some integer, and k we were told is 0.720 pi radians. I'm only got that 0. And we can see here that our pi's cancel. So we're left with just n times 1 over 0.72. And that comes out to n times 1.33. So our nodes are at x is equal to 0, x is, because we said 0 is definitely a node, right? Then we said 1.33, so x is equal to 1.33 is a node. Then 2 times 1.33 will be a node, so we'll have 2.66. Then 3 times 1.33 will be a node, so we'll have 3.99, and on into infinity. So those are the locations of our nodes. Now it also wants to know what is, so the antinodes as well. We want to find the location of the antinodes. So for the antinodes, we want it to be either at a maximum, or remember we have a standing wave, so we'll oscillate like that too. So it either has to be at a maximum up here, or at a minimum down here, right? These are where the antinodes are. So the antinodes oscillate from the maximum amplitude all the way down to that minimum point. So the antinodes, we want sine kx to be equal to plus or minus 1, right? And now, where is sine plus or minus 1? Well, sine is plus or, oops, this is my sine graph. Sine is plus or minus 1 at pi over 2, 3 pi over 2, 5 pi over 2. So this happens when sine is n plus 1/2 pi. Okay, so now we can see that kx has to be equal to n plus 1/2 pi. So kx will be equal to n plus 1/2 pi, and that will give us the location of every antinode. So then just solve for x again, and we get n plus 1/2 pi over k. And we know n plus 1/2 pi. K was 0.72 pi, so our pi's cancel. And we get left with now n plus 1/2 times 1.33. So for n is equal to 0, that ends up just being 1/2 times 1.33. So our antinodes are at 0.665, and then you'll have 1 plus 1/2 times 1.33, so 3/2 times 1.33. That will give you 1.995, and then plug in 2 here, so you have 2 plus 1/2. That will give you 3.325, and again, so on, all to infinity. So that's how you calculate the location of a node and an antinode. You just want to find where sine kx is equal to 0 for a node and where it's equal to plus or minus 1 for an antinode. All right, now we're going to do an example with intensity, because I know a lot of people did not like intensity in sound. So this was from your homework. So let's go over this problem here. So we have a lion can produce a roar with sound intensity level of 114 decibels at a distance of 1 meter. So when you're 1 meter away from the lion, hopefully like not in the wild, you have a sound intensity level of 114 decibels. So what is the sound intensity level at a distance of 4 meters away? So first let's write down our sound intensity. So I'll leave out the decibels here so it's a little bit clearer. And I naught is just some constant that's 10 to the negative 12 watts per meter squared. So there's a couple different ways to solve this problem. I'm just going to do the way that like came to me first. There's obviously other ways to do it. So, as long as you get the right answer, that's fine. So the first thing I said was, okay, I know the sound intensity level is 114 decibels, 1 meter away from the lion. So I know beta. I know I naught because it's just a constant. I don't know the intensity of the lion's roar 1 meter away, but I know what intensity is, right? It's the power divided by 4 pi r squared. So what I wanted to do was just find this power, because the lion's roar is going to output the same amount of power whether you're 1 meter away, 4 meters away, or 15 meters away. It's just the intensity will go down. So I know that the power that the lion's outputting isn't changing. So I wanted to just find the power. That way then I could just plug, I could find the intensity for each distance by changing r, and then plug that intensity just into this formula, and that would be all I have to do. So We have to do a little bit of algebra for this, so let's find the power output with our initial 114 decibels. So we have, I'll just write it like this. We have 114 decibels. We have 10 times log. The intensity is the power over 4 pi r squared, I naught. And then I can just solve for power now, right? Because I know that I naught I can replace with 10 to the negative 12. And in this first case, we're only 1 meter away. So this r squared is just 1. So I can just write, I just have this equation here. So what I'm going to do first is divide both sides by 10. So I get 11.4 is log of p over 4 pi 10 to the negative 12. And so now we're just going to have to solve for p. So when you have your variable in here trapped inside your log, what you want to do is just have everything 10 raised to the power of like each side of your equation. You're just going to take 10 and raise it. So here we're going to have 10 to the 11.4. And then here when you take 10 to the log, 10 to the log of something cancels out. So these two things are actually just going to cancel out, and you're going to be left with 10 to the 11.4 is equal to p over 4 pi 10 to the negative 12. And then you can just plug this into your calculator, cross multiply and solve for p, and you'll get that the power output is 3.15 watts. So this is the power output by the Lion. And then now that I have the power output, I can just plug that back into this equation and instead use 4 meters. So for part A, I'm just going to do 10 log. The intensity is the power divided by 4 pi r squared, where r now is 4. And then the intensity, I naught, is 10 to the negative 12. So then I just do that. Again, just plug all this stuff into your calculator, and you end up with 102 decibels. So this is obviously lower than the decibel level when we were 1 meter away, and that makes sense, right? Because if we're only 1 meter away from the Lion, we expect it to be have a much higher sound intensity level than if we're 4 meters away. And now when we do part B with 15.8 meters, we expect it to, again, we want to get an answer that's, again, even lower than 102 decibels because now we're even further away. So now I can just do the exact same thing. So we're going to have 10 log, the power stays the same at 3.15, and then we just do 4 pi, 15.8 now is the radius, so it's the radius squared there, and then times the intensity, I naught, is 10 to the negative 12, and this comes out to 90 decibels. So now we get 90 decibels, so this all makes sense physically. You would expect the loudest sound intensity to be 1 meter away, and then for that to decrease as we go to 4 meters, and then 15.8 meters. So like I said, there's different ways to do this. The book has another solution in the solution manual. This is the way I did it. So all I did here was I just know that the power output by the Lion is not changing, so I just solved for that first, and then I was able to just replace intensity with P over the area, right? We said intensity was the power divided by the surface area of like that imaginary sphere that's radiating outward with the power. So then I just plugged that in. Instead of the intensity, I plugged P over 4 pi r squared, and then I was able to just calculate my decibel level like that. All right, now let's do another problem, but this time, let's do this one. I think this was also a homework problem. Okay, so we have a particular open organ pipe has a fundamental frequency of 220 hertz. When the speed of sound waves in air is 344 meters per second, what is the length of this pipe? Okay, so we have a fundamental frequency. So for part A, they're telling us the fundamental frequency for an open pipe. So remember, the frequencies for an open pipe look like this, NV over 2L, because an open pipe can support half wavelengths only. So we have NV over 2L, and they're saying that the fundamental frequency, which is when n is equal to 1, so n is equal to 1 is the fundamental frequency. So that means that when n is equal to 1, V over 2L is equal to 220 hertz. Or here, I'll do it this way. So we want to know the length of the pipe. So we can just plug here, and here we know F1. They're telling us the fundamental frequency is 220 hertz. We know the velocity of sound and air. Then we just have to find L. So all we have to do here is just solve for L, and we get the length is equal to V over 2F. And this comes out to, we do 344 divided by 2 times the frequency was 220, and that comes out to 0.782 meters. So the length of the pipe is 0.782 meters. Another way you could think about this is when we have an open pipe, it's going to look like that. And the fundamental frequency is basically fitting the minimum number of wavelengths into it, which is 1/2 wavelength. Because we know that an open pipe is going to have an antinode at each end. So the fundamental frequency for an open pipe is going to look like this, where we have an antinode, node, antinode. And we know that there's 1/2 wavelength in there. And then we could use this formula, V is equal to lambda F. And we could use this to find lambda, and then we know that the length of this is going to be L over 2, right? Because if it's the fundamental frequency, this is half a wavelength. And then you can plug in for lambda here. We can rewrite this as 2L is equal to lambda. So we'll have V is equal to 2L times the frequency. And then to solve for L, you can see we'll get the same exact expression. We'll get L is equal to V over 2F. So either way you think of it, you end up with the same answer. So it's important to note here that it says it's an open pipe, so that means I'm going to be using this formula because this is the formula for the harmonics of an open pipe. And I also know that for an open pipe, it has an antinode at each end. So I know that the fundamental frequency has to look like this, and it has to be 1/2 wavelength because we need an antinode at each end. All right, then for part B, the third harmonic, so that means n is equal to 3 is the third harmonic. This pipe has the same frequency as the fundamental frequency of a stopped pipe. What is the length of the stopped pipe? So for a stopped pipe, the frequencies, or the harmonics, are given by NV over 4L. Because remember that our stopped pipe could support quarter wavelengths. So this is our stopped pipe formula. And they're telling us that the fundamental frequency of the stopped pipes, that would be when when n is equal to 1. So the fundamental frequency here is equal to the n equal 3 case of the open pipe. So we have F3 is equal to 3V over 2L, and we have F1 in our closed pipe, or our stopped pipe, is this. And they're saying that these are equal to each other, right? The frequencies are the same. So we can just set this equation and this equation equal to each other. So we have 3V over 2L is equal to V over 4L. And I should be careful because these are two different lengths, right? I'll use length of the stopped pipe here, and this is our open pipe. So these are two different L's, so we have to be careful of that. But the velocity of sound is the same, so these V's will cancel. And I want to find this L. So I can just solve for this L. Let's see, we'll have 12, if I cross multiply 12, LS is equal to 2LO. So that means that LS is equal to LO over 6. So all I have to do is take the length of my open pipe, which I had here, right, the 0.782, and divide by 6. So that gives me 0.782 divided by 6 is 0.13 meters. So this is the length of my stopped pipe. So the important thing here again to remember is that stopped pipe and open pipes have different forms of their harmonics, right? So this is all of the harmonics for an open pipe, and we have the 2 at the bottom. For the stopped pipe, we had a 4 at the bottom. And the fundamental frequency always refers to the n equals 1 case. When we talk about harmonics, it just goes by, whatever number n is, it's that harmonic. So n equals 3 is the third harmonic, n equals 5 is the fifth harmonic, n equals 10 is the 10th harmonic. That's different from overtones. Remember, overtones are a little bit more confusing, where they refer to the tone over the fundamental. So for overtones, you can have the fundamental frequency, and then for n equals 2, that's the second harmonic, but also it's called the first overtone. So the second harmonic and the first overtone are the same thing because it's the first tone over the fundamental. Then if you have n equals 3, that would be the third harmonic or the second overtone. So this is also the second overtone. Then for n equals 4, fourth harmonic, third overtone. So that's a little bit confusing. It's just, off by 1 basically. So when you hear overtone, third overtone, it's just plus 1. It's the fourth harmonic. N equals 4. And then also remember, for stopped pipes, we only have odd harmonics. So a stopped pipe will only have n is equal to 1, 3, 5, 7. You'll never have like the fourth harmonic for a stopped pipe. It's always odd. Whereas for an open pipe, you can have any value of n. So any integer is fine, but for a stopped pipe, it has to be odd. All right, now let's just do quickly one more problem that was from, I think, your homework. Okay, so here we have the pattern of displacement nodes N and antinodes A in a pipe is this, when the standing wave frequency is 1,710 hertz. The pipe contains air at 20 degrees Celsius. They're just telling you basically look up the speed of sound. I think they're just using 344 again. Yeah, so that's just going to be 344 meters per second for the speed of sound. Which harmonic is this? So the first thing I would do here is just draw out what this corresponds to. So I'm going to count my nodes here. So I have 1, 2, 3, 4, 5 nodes. So I'm just going to draw a standing wave. So it starts with an antinode. So I'm just going to draw like a bunch here. And we'll count 5 nodes. So we have, starts with an antinode, we have 1 node, 2, 3, 4, 5. Okay, so we've got 5, and then it ends at an antinode on each end. So this part in here, let's erase this out here. Oops. So here, oops. So here, this corresponds to this pattern because we have an antinode on each end, right? It starts and ends with an antinode, and then we have 5 nodes in between, and then an antinode in between each node. So they want to know first, is it an open or closed pipe? Well, it's open because we can see it has an antinode at each end, and you can see that right from here. It has an antinode on each end, so it's an open pipe. So this is open. Then for part B, which harmonic is this? So we know that the harmonics for an open pipe, we said the harmonics, remember it can support half wavelengths. So I see here, this is 1/2 wavelength. This is a half wavelength. This is a half wavelength. This is a half wavelength. And this is a half wavelength, right? So from antinode to antinode is a half wavelength. So I see 1, 2, 3, 4, 5. So I see 5 half wavelengths. So that means it's my 5th harmonic. It can support 5 integer numbers of half wavelengths. So n equals 5. So this is the fifth harmonic. Or the fourth, that's also the fourth overtone. All right, now we want to know what is the length of the pipe. So we know now that it's the fifth harmonic, and we know that the frequencies of the harmonics are given by NV over 2L for an open pipe, and we know that N is equal to 5. And we know that the speed of sound is going to be 344, so we can just solve for L here, because they also tell us the frequency. So we know that, let's see, F5 is equal to 5V over 2L. And we just solve for L. We get L is equal to 5V over 2F. And so then L is 5 times 344 divided by 2 times the frequency they gave us, because they told us the frequency here is 1710. And so you just plug that into your calculator, and for this, we get 0.502 or 582. I can't read my own handwriting. It's either 0.502 or 0.582 meters. Okay, so this is the length of the pipe. And then, okay, so that's it for part C. And then we want to know, what is the fundamental frequency? So the fundamental frequency we know is when n is equal to 1, right? So the fundamental frequency is when n is equal to 1. Is the fundamental. And so then we just plug that into this equation with n is equal to 1 now that we know the length, and we find the fundamental frequency. And remember, we're going to expect the fundamental frequency to be lower than this, because the fundamental frequency is the lowest frequency, and then all the other ones are higher than that, right? So we expect this to be somewhat lower than 1710. So we have So we're going to have 1 times 344 divided by 2 times the length, which is, I'll just say 0.5. And then we plug that in and we get 342.6 hertz. So this is our fundamental frequency in this open pipe. And then this was a homework problem, and I didn't realize that it asked you to take into account the temperature for part E, so I just gave everyone credit for that because we didn't cover that in lecture. So if you tried it, good. If you didn't, you get credit anyway. Okay, so for part so obviously nothing like that will be on the exam with temperature because we didn't do that. Okay, so this is all we're going to review with harmonics and fundamentals. Remember, for these, the big thing to remember is this formula for an open pipe, but it's on your formula sheet. It even says open pipe, so there's really not too much to remember there. Then the important thing to remember for an open pipe is that it has an antinode at each end, because that is not on your formula sheet. And then for a closed pipe or a stopped pipe, this is the formula. Again, on your formula sheet, it says stopped pipe, so nothing to remember there. And a stopped pipe will have a node at one end and an antinode at the other end. So let's say if this problem didn't have this A here, it would be a stopped pipe. All right, so let's go on now to the Doppler shift, because that was the other big thing that people were not happy about. So let's look at some Doppler shift problems. So I don't think this was a homework problem. So before we get to this problem, I just want to go back over the sign rules. So if you go to our chapter 16, part 2 notes, so 16, part 2, I added in the sign convention at the end of the full notes. So here we have the sign convention for a Doppler shift. So just say, whatever listener and source you have, call your positive direction the direction from the listener to the source. So whatever direction that's in, call that the positive direction. And then if the listener moves towards the source, that's a positive for the velocity of the listener. If the listener moves away from the source, so if the listener is moving this way, that's a negative. If the source moves towards the listener, that's a negative. So if this source starts moving in this direction, that's a negative velocity for the source. And then if the source moves away from the listener, that's positive. So basically, all you're doing here really is just choosing your positive direction to be from the listener to the source, and then everything else is the same as it normally would be when you're deciding the sign of a velocity. If you're going in the positive direction, it's positive. If you're going in the negative direction, it's negative. So really all you have to remember here is from listener to source is your positive direction. Okay, so now let's do that Doppler shift problem. So here we have, while sitting in your car by the side of a road, you are approached by your friend who happens to be in the same car. You blow your car's horn, which has a frequency of 260 hertz. Your friend blows his car's horn, which is identical to yours. Whoops, and you hear, I cut off again. You hear a beat frequency of 6 hertz. How fast is your friend approaching you? So, let's just draw a little picture. So you're sitting here, you're the listener, and you're obviously moving with 0 speed since it says you're sitting still. And the frequency, let's see, so then your friend is moving towards you with some speed that we don't know. And so remember, we call the direction from listener to source the positive direction. So in this case, this would actually be our positive direction, right? Because we go from the listener to the source is our positive direction. So we have the frequency of the source is 260 hertz. So now it says that we hear a beat frequency when our car horn is honking, and when the friend's horn is honking, we hear a beat frequency of 6 hertz. So remember, F beat is just the the difference between the two frequencies. So it'll just be like FA minus FB. So in this case, since our friend is moving towards us, we know that that frequency is going to be higher, right? Because we just know that from everyday life, when you hear like a siren coming towards you, the frequency gets higher. So we know that the friend's horn is going to be FA and our horn here will be FB. So 6 beats is equal to the frequency of the listener. So that's the frequency that we hear, because we're the listener. So we hear our friend's horn at some higher frequency. And then the frequency of the source, which is our horn, is that 260. And we don't know what this frequency is yet. We don't know what the frequency of the listener is. And we don't know how fast he's going. So now we have to use the Doppler shift to figure out what this FL is. So plug in the Doppler shift here. So the frequency of the listener is V plus minus VL, and then V plus minus Vs times the frequency of the source. So here, the listener, we already said, is not moving, right? We're the listener, and we're not moving in our car. So this is 0. And then the velocity of the source, we don't know, so this is what we're looking for, but we can't figure out if it's positive or negative, right? So we said that the positive direction is from the listener to the source, and here our source is moving opposite that, right? He's moving towards us, so this is going to get a negative. So down here, this will be a negative. And we know the speed of sound in air is 344, and we know the frequency of the source, because we know that he has the same horn as us, so we know that the frequency of the source is 260 hertz. So now we can just plug this in to here and then solve for Vs. So we're going to have the 6 beat frequency is V over V minus Vs times Fs, and then minus 260, and then we just have to solve for Vs here. So this is going to take a little bit of algebra. So let's move this to the other side. So we get 266 is equal to V minus Vs. And then we can cross multiply, so we'll do that over here. So we get 266 V minus Vs is Vfs. And then we can do this. And then we'll divide by 266. So we'll have 266 times, actually, and then we can simplify this a little bit. So I'll have V 266 minus Fs over 266 is equal to Vs. Okay, so now we can plug everything in. So V is the velocity of sound in air, so that's going to be 344. 266 minus the frequency of the source. The frequency of the source is 260. So that's 266 minus 260 is 6, divided by 266 gives us the velocity of the source, and that comes out to 7.8 meters per second. Okay, so this is how fast our friend is moving towards us. So if he's moving this fast towards us, his horn beeping at 260 hertz and hours will create a beat frequency together of 6 hertz because of the Doppler shift. So here the confusing and most important thing is your signs. It's always important to get your signs right, because if you get your Doppler shift signs wrong, it's not gonna work out. And then the other thing is to just keep who is the listener and who is the source here. So we're the listener because we're listening to our friend's horn, and we have the same frequency horn, right? They're both 260 hertz, so we're going to hear a slightly higher frequency from him because he's moving towards us. And this will create a beat frequency that we can hear. All right, so now we have one more Doppler shift problem. So this one is a little bit harder, and this is with a little bit of a double Doppler shift. So here we have a stationary police car emits a sound of frequency 1200 hertz that bounces off a car on the highway and returns with a frequency of 1250 hertz. The police car is right next to the highway, so let's say the police car is like right here hiding in the bushes, and then you're traveling like this. So the velocity of the listener is 0, the velocity of the source, we don't know yet. So we have, okay, so he has, let's see, then the frequency of the listener, he hears 1250 hertz. Okay, so let's see, how fast was the moving car going? So what we have here is a double Doppler shift because he's the original source, right? So we have the original source. Let me change these actually to the velocity of the car and the velocity of the police officer, so it's not confusing. This is the frequency of the police officer that he hears. We'll call that F prime, because that's what he hears back. So he initially emits a sound where he's the source. So he's the source and emits a sound of 1200 hertz. It goes to this car, which is moving towards it. So the listener is moving here. The car will have, he'll hear some sound slightly higher than 1200 because he's moving closer to the source, so the frequency would go up. And then it bounces off this car. So now this new Doppler shifted frequency, so now this Doppler shifted frequency is going back now where he's the source and the cop car is the listener. So you have basically two Doppler shifts, one to get to the moving car and then one when it's reflected back again. So let's set this up carefully. So let's do initially, we have the frequency. So when the frequency of 1200 hertz goes from the cop car to this car. So we're going to call this is the source and this is the listener. So that means that from our listener to our source, this is the positive direction. So we have the frequency of the listener, which in this case is the car. So the frequency of the car that the car hears is V plus minus V of the car, V plus minus V of the police, and then the frequency that the police initially outputs, which is that 1200. So let's get our signs right. So here the cop car is not moving, right? So this is 0. And then we said that the car, to go from listener to source, is the positive direction, and the car is moving in the positive direction. Oh wait, is it? No, we don't know that. Sorry, so we don't know if the car is moving to him or away from him. So what we can do is just call this positive. So since here we don't actually know if he was moving towards or away from the car, so cop cars, we don't know if he was moving here or had already passed the car and is moving this way. Just pick one, And if our final answer is negative, then we know that we picked wrong. So in this case, I'm assuming that he's moving towards the cop car. So let's say if my final answer ends up being, positive 5 meters per second, I know that I picked right. If it ends up being negative 5 meters per second, that means that I picked wrong and he's actually going away from the cop car. So I'm just going to pick positive here. So we're going to have that be positive. So now this frequency is the 1200 that the police car emitted. This is the velocity that the car is moving at. This is the frequency that the car hears once it's been Doppler shifted from here to here. And this velocity is the velocity of sound. So now what I can do is write another Doppler shift where now the car is the source and the police officer now is the listener, right? Because he's listening for that sound back. So now I'm going to call that VP prime because that's like the new sound that the new frequency that the cop car hears. So we have V plus minus the police officer in the top now because he's the listener. V plus minus velocity of the car, and then the frequency that the car heard. So let's look at our signs. So the cop car again is not moving, so this is definitely 0 up here. And so now here, since the cop car is the listener, right, that means to go from listener to source is actually this direction. So now this is our positive direction, but the car we said is moving, this way, right? So we don't want to change what direction we said the car is moving in. So the car is still moving in this way, except now this gets a negative sign because now the car is the source and he's moving towards the listener. So that means it gets a negative sign down here. So this becomes negative. And now what we can do is we can figure out, so we know this is 1250. So this is 1250 hertz. We're still looking for VC, but this frequency that the car hears, we can just replace this with this. So I'm going to rewrite this frequency that the cop heard, V over V minus VC. And now I'm going to replace FC with this expression. So that's going to be V plus VC over V times the frequency that the police originally emitted. So this is the 1250, this is the 1200. I can see here that my velocities here cancel. So I'm left with V plus VC over V minus VC times the frequency of the police officer. So let's just solve for the velocity of the car. So I'll just, let's just cross multiply. So we get V minus VC times FP prime, and then V plus VC FP. And now we can do this. And now I'm just going to move the terms, let's move all the terms with the car to one side and all the terms without the car to the other side. So I'm going to have VP prime and then minus V FP, and then this will be equal to VC FP plus VC FP prime. Okay, and now I can simplify this. And now I can divide both sides here. So I get the velocity of sound. And then this is FP plus FP prime. This is equal to the velocity of the car. Okay, so there's a lot of algebra there, but this is our final answer. Now we can just plug in numbers. So here now, I'm just going to plug in for the velocity. We'll just plug in 344. For, remember, FP prime, so this is the frequency that the cop car hears once it's been reflected. So that is the 1250 hertz there. So I'm going to plug in 1250 minus the original frequency he outputted, which was 1200, divided by 1200 plus 1250. And we end up there with about 7 meters per second. So this is how fast our car is moving. Okay, so that was, I mean, this kind of problem is going to be like the most difficult Doppler problem that you would, the type that you would see, where not only is it a double Doppler shift, but you kind of have to solve for something that's like sort of buried in the Doppler shift, like one of the velocities. So if you can follow along with this and you feel comfortable with this problem, you're probably good with Doppler shifts. Now let's just do this part B. So we're saying, oh, and then also here, since we got, since we got a positive answer for our velocity, that means we picked right, and the car was moving towards the police car like this, not away from him. Another way also that you could figure that out is that we can see that the frequency that the police car hears back is higher, so that means that this guy is moving closer to him, because if you hear a higher frequency, that means that you're getting closer together. Okay, so let's do part B now. So what frequency would the police car have received? It had been traveling towards the other car at 20 meters per second. So now the police car is moving also towards this car at 20 meters per second. So let's just draw a little picture. So we have our car is traveling this way at 7, and now the police car is also traveling this way at 20. So let's first do the Doppler shift from the cop car to the this car. So we're going to call him the listener. So from the listener to the source is in the positive direction. So our car is the listener first. And let's just see what frequency first the car hears, basically. So f of the listener is v plus vl, v plus minus vs. Okay, so here our listener is moving towards the source. So this is positive. But then our source is moving in the opposite direction, right? We called this our positive direction. Our source now is moving in the negative direction. So this gets a negative. Okay, so now we can just plug things in. We have 344 as the speed of sound, plus the velocity of the listener, which we said was 7, as calculated up here. And then 344 minus 20, because the cop car is moving towards us. And then times the frequency of the source, which is 1200. So just plug those things in, and we get 1300 hertz. So now this car hears 1300 hertz from what the police car outputs. So now this frequency gets reflected back to the cop car. So now the car over here is the source, and the cop car is the listener. So let's reverse our direction from listener to source. So now the listener is the cop car. So from listener to source is positive direction. So our positive direction flips now. And so now let's do FL. So this is like FL prime maybe. V plus V listener, V plus minus V source, F source. Okay. So now our listener is the cop car, and he's moving obviously in the positive direction. So this stays positive. And now the source, which is bouncing that frequency back, the source now is moving in the negative direction, right? Because he's moving from source to listener, so that's the negative direction. So this gets a negative. And now we can just plug things in. So the velocity of sound is still 344. Plus the velocity of the listener, which is the cop car now. So that's plus 20. And then 344 minus the velocity of the source, which is now the car, which is 7, times the frequency of the source. And the source now is this frequency that's reflecting back. So the source is now 1300. And now you just plug those things in, and for that you get 1404 hertz. Okay, so that would be the frequency that the police car heard if he was moving towards this other car at 20 meters per second, and the other car was also moving towards him at 7 meters per second. All right, so that's it for our review. If you can do these problems and you find them, like reasonable, you should be fine on the exam. I try to make my exam very similar to the problems we do in review, in discussion, in homework. So if you're okay with these, you should be okay. Okay, so that's it. So I will see you guys on Thursday for our exam. And again, if you have any questions at all about how the exam is, the proctoring or anything like that, just email me. I would rather just get a lot of emails than have something go wrong in the exam. So don't be afraid to email me leading up to the exam. And yeah, so I will see you guys then, and good luck.